Hi there. Now we can start looking at what happens when atoms come together. And we're going to start our discussion focusing on metals. So, metal atoms, as we've seen, tend to have low ionization energies and moderate electron affinities. And as an example, we're going to look at sodium. So, sodium is one of the alkali metals. It has a single valence electron in the 3s orbital. And if a bunch of sodium atoms were to come together, because the atoms have a very low ionization energy, the valence electrons are held quite loosely. And so as the atoms come together, those loosely attached valence electrons can come loose and sort of float around and be attracted by all of the atomic cores. And so the effect is that you've got the core of the sodium atom, which has a net charge of +1, and then you've got the valence electrons kind of floating around, being attracted to all of those atomic cores. And so the electrons are sort of acting like a glue that holds the set of atomic cores together. And the attractive forces between this sea of valence electrons and the atomic cores tends to pull the atoms into an orderly arrangement called a crystal lattice. And the result is that at room temperature, sodium exists as a solid metal. And the sodium atoms are arranged in a crystalline format. And this is characteristic of what's called metallic bonding. Whenever a bunch of metal atoms come together, whether they're all the same or whether they're different metal atoms, the result is a picture like this, where the valence electrons come loose and sort of float around in a sea of electrons, holding the cores of the metal atoms together. And the result is a solid which tends to be fairly easy to deform, and so it's soft, it's ductile, and malleable. And also, because the valence electrons are free to move throughout the metal, these solids are highly conductive. They conduct electricity really well. Now, something very different happens when metal atoms approach nonmetal atoms. And so if we stick with the sodium as an example, but if we imagine a couple of sodium atoms encountering a couple of chlorine atoms, chlorine is in the same period of the periodic table. It's in row 3, but it's at the other end. Chlorine has 7 valence electrons, and because it has a much higher charge in the nucleus, the chlorine atom is significantly smaller than the sodium atom. The nucleus is more positive, the valence electrons are pulled in more closely. And as we've seen, chlorine has a much higher ionization energy. Its valence electrons are held much more tightly than they are in something like a sodium atom. Chlorine also has a high electron affinity. It has a high tendency to take on new electrons. And so the upshot is, when a bunch of sodium atoms encounter a bunch of chlorine atoms, the valence electron on each sodium atom easily comes loose and starts floating around. And so you have a situation where you have the sodium cores with their net positive charge. You've got the sodium valence electrons loosely floating around, but then because the chlorine atoms pull in electrons so strongly, chlorine has a high electron affinity, those floating valence electrons just get soaked up by the chlorines, turning them into chloride ions. And so the overall effect is that each sodium atom loses its valence electron, which then gets transferred to a chlorine atom. And so now you've got ions. The sodium atoms have fully lost their valence electron, forming positive sodium ions. The chlorine atoms have taken on an additional electron, forming negatively charged chloride ions. And then the resulting forces that attract these ions together pull them into an orderly arrangement, just like we saw in the case of sodium, except here, instead of positive atomic cores being held together by a sea of electrons, we've got positive ions being held together by their attraction for negative ions. And the result is a three-dimensional crystal lattice of ions, of sodium and chloride ions. And this is the familiar sodium chloride that we are familiar with. And ionic solids like sodium chloride tend to be much more brittle than metals. They don't deform as easily. They tend to break rather than deforming. And also, because those valence electrons are now locked up in the chloride ions, ionic solids like sodium chloride cannot conduct electricity. They are electrical insulators. So let's look at another example of ionic compounds forming between a metal and a nonmetal. This time we're going to look at calcium, which is an alkaline earth metal. It's in the fourth row of the periodic table. And we're going to imagine calcium encountering nitrogen. Nitrogen forms diatomic molecules that are a gas at room temperature, but you can liquefy nitrogen and store it in containers like this one. Calcium, as an alkali metal, has two valence electrons. These are in the 4s orbital. And just like in the case of sodium, calcium can readily lose its valence electrons. It doesn't hold them all that tightly. It has a low ionization energy. So it can lose its two valence electrons, which can then be taken on by the nonmetal nitrogen. And so nitrogen has 5 valence electrons, and it has room for 3 more. And so when nitrogen forms an ion, it will take on 3 new electrons to form the N3 nitride ion. And so since each calcium atom can only provide 2 electrons, and each nitrogen atom is taking on 3 new electrons, the calcium and the nitrogen are going to combine in a 3-to-2 ratio. And so the result is an ionic compound, calcium nitride, which is Ca3N2. And so in the formula unit, 3 calcium atoms produce, they're able to free up a total of 6 valence electrons, and those 6 valence electrons are taken on by the 2 nitrogens to turn them into the N3-. And you may be wondering why nitrogen is willing to take on these electrons. After all, we talked earlier about how nitrogen actually is not all that attractive to electrons. In fact, the electron affinity of a nitrogen atom is slightly negative. And the answer is, if you just had a single nitrogen floating around in space, it wouldn't want to take on a new electron. But because you've got this mixture of the calcium and the nitrogen, as the electrons are exchanged, you're forming these positive and negative ions, which are tightly attracted to each other. And the resulting formation of the ionic lattice with these really strong attractive forces between the ions, that's ultimately the driving force that causes the nitrogen to take on electrons, even though if it were by itself, it really wouldn't be interested in taking on additional valence electrons. And so that is the picture that we've got with calcium nitride. And then another thing that we saw with the sodium chloride that we're also seeing here with the calcium nitride is that if you think about the electron configuration of the calcium atoms, they've lost their valence electrons, and that leaves them with their electronic core, which has a configuration of like that of argon. And then nitrogen has taken on 3 more valence electrons, and so it now has an electron configuration that resembles neon. And so after this exchange of electrons to form ions, the calcium has ended up with a noble gas configuration of electrons, and the nitrogen has ended up with a noble gas configuration of electrons. And this is very typical, especially when you've got metals and nonmetals that are main group elements. That is, elements in the S block and in the P block of the periodic table. When these elements form ions, they tend to take on noble gas electron configurations. And as we saw before, noble gas electron configurations tend to be quite stable. Once you have a noble gas electron configuration, your electrons are going to be held pretty tightly, and you're not going to want to lose them. And so by forming noble gas electron configurations, metals and nonmetals are able to form stable arrangements of their electrons. Things do get a little bit more complicated with the transition metals and the inner transition metals. And so in the next graphic here, I'm summarizing the behavior of all of the different atoms when they form monatomic ions. So atoms many of the atoms can gain electrons or lose electrons to form individual ions. Not all atoms will do this. Noble gases don't form ions readily. Metalloids don't really like to form ions very much. Not a whole lot is known about the last row of the periodic table or about the inner transition metals, so I've kind of left them out of the graphic. But among the elements that do readily form ions, we can see that the nonmetals tend to take on electrons until they have filled in their valence shell. So the halogens tend to take on a single electron when they ionize. The chalcogens tend to take on 2 electrons. The pnictogens tend to take on 3 electrons when they form ions, and carbon tends to take on 4 when it forms the carbide ion. And then in the alkali metals and the alkaline earth metals, they tend to lose their valence electrons, and then that pattern continues for a little ways into the transition metals. In fact, the first 5 groups of the periodic table have a tendency to lose all of their valence electrons when they form positive ions. But then it's in the middle of the periodic table where things get a little weird. And what we end up seeing is that if you look at the rest of the transition metals, almost all of them tend to form ions with a +2 charge, and then some of them can also form different charges. And so those elements that are kind of broken represent atoms that have a choice of forming ions with different charges. And so, for example, chromium can either form a +2 ion or a +3 ion. It can lose 2 electrons or it can lose 3 electrons. And so for all of those transition metals in the middle of the periodic table, as it turns out, the reason that they can all, or almost all of them, can lose 2 electrons is that they will lose their s electrons and hold on to their d electrons. And this is sort of counterintuitive because we talk about in the Aufbau principle that the d electrons come in after the s electrons. But when electrons are lost by transition metals, it's the s electrons that go first. And I don't have a nice explanation for why that is. That's just what seems to happen with these metals. And so for all of those metals in the middle of the periodic table, they will all tend to lose their s electrons, and then sometimes they will lose a d electron as well. So for example, iron, when it forms positive ions, can easily lose its two s electrons to form Fe2+, and then it will sometimes lose one of its d electrons to form Fe3+. And so you have this general pattern where all of these transition metals in the middle of the periodic table, they can all fairly easily lose their s electrons, and then they can also often lose one of the d electrons. They won't continue losing d electrons because the charge of the nucleus eventually stops electrons from being lost. You won't just lose electrons forever. And with these intermediate metals, the s electrons will go, and then one of the d electrons may also go, and so you'll typically have metals that have a choice of which ion they're going to form. And then once you get to back into the p block and aluminum and the metals below it, they tend to hold on to their d electrons, just like those transition metals, but they will lose their s electrons and the p electron that's in aluminum, gallium, indium, and thallium. And then the rest of the metals, tin, lead, polonium, and these other guys, they will lose their p electrons, and they'll sometimes lose their s electrons. And so the result is something like lead can form either a 2+ ion or a 4+ ion. And so if you have a general understanding of these patterns, then a lot of the reactivity of the metals and nonmetals when they form ionic compounds will make a lot more sense. So that will finish up this part of the story, and we will continue our discussion of chemical bonding with a look at covalent bonding in the next video.